through this series, we've just been looking at some of the possible pitfalls and gremlins which can impact a coating project. We spent some fairly in-depth time looking at the documentation side, where we need to keep our eyes open to make sure that our documentation will withstand the rigors of the experience. We spent time in the last two sessions looking at both surface preparation and coating application, and some of the gremlins we can encounter when we're actually getting our hands dirty. And if you recall, we said that we would now take some time to look at how we can monitor what we have done and what pitfalls we should be aware of. So today we're going to talk about measurements that we take when we're on site. And I'm delighted to welcome Gert Conradie back into the hot seat to have this discussion with me. So welcome, Gert. Perhaps before we talk about coating thickness, maybe we should start with the profile, because I'm sure that has an impact on the coating thickness itself.
Most definitely, yeah. Let's talk about before you can put any coating on top of the surface, you obviously need to make sure that it's going to stick to something. So I think it's important that we just talk a little bit about the actual profile, because it can also affect the quantity of paint that you are using.
So I know that when we spoke about surface preparation, we spoke long and hard about cleaning our surface, making sure that it met the SA 2.5 or SA 3 standard. But I'm sure that there's more to cleanliness than that, which is a visual specification, especially after we've blasted.
Most definitely, and I think this is where the first gremlin actually starts setting in, because when people hear a standard and they see SA 2.5 or SA 3 or SA 2, they want to try and connect that to how rough the surface is. And it doesn't talk about roughness at all. When you refer to that standard, it only talks about how clean the surface needs to look when you are visually assessing it. Is it visually clean? Is it very thorough? Is it thorough? So there's no profile that it actually talks about. So when we talk about anchor profile, that's the term now that describes the roughness of the substrate, consisting of craters or cracks or pores, and as the word describes anchor, it does exactly what a boat anchor does. It takes that coating and it gives it something to hold onto. And sometimes think that, when you visually look at it, now again, going back to that SA 2.5 or SA 3, there you can assess how clean the surface is. But when you're looking at anchor profile, you can't visually actually represent how rough the surface is. You have to measure it somehow. And that's where your different standards comes in. So you've got ISO 8501-1, that talks about SA 2.5 and 3 and all of those. And now you've got ASTM D4417 or ISO 8503. That is the most commonly specified standards for non-destructive testing of what is the anchor profile or the roughness of my system. Basically, if we look at our pre-blasted surface, the reason why we need to blast the surface is for it to hang on to something.
Okay, that makes sense. So we've blasted the surface, and I know, having physically felt, and now obviously the surface isn't clean, but the surface for a roughness, you can feel whether it's very sharp or whether it's like smooth sandpaper.
I'd like to share my screen with you and actually give you a representation of what we are looking at when we say we're looking at a blasted surface. When you look at this actual representation, it's only a 5 micron enlargement of what you're seeing on top of the surface. As somebody else had pointed out and helped us with our videos and recordings, said it looks like a beautiful forest.
It does.
It almost does, because what we have now done, we've roughened the surface, and quite rightly, as you have described, you can see these peaks and you can see these valleys. So when we measure the profile, where are we measuring? What's the representation? So again, just like when we spoke about it earlier, you cannot take any measurement and a single measurement say, look, now I can pass or fail this area for being rough enough or clean enough or thick enough or whatever it might be. You have to get a representation of an entire area. And what we have done, and the reason for doing it, and getting to explain the anchor profile, if you look at this 250 micron pixel representation that you see here, if you've got a string of line all across these peaks and valleys, you have effectively actually tripled or maybe quadrupled the surface area. And this is the reason for putting on the anchor profile, whether it be an angular profile, as you see here, or a peened profile if you maybe shot blasted the surface. And that's the reason to want to record these.
I know that one of the ways we can measure the profile is by using a profile gauge. And another way that I think many people are familiar with is replica tape. Are those the only ways we can measure profile?
There's actually 3 different methods of measurement. And again, I'd like to share my screen with you. In accordance with ASTM D4417, the 3 most common methods that are used is using something called a comparator. And a comparator is basically a steel panel that's more or less about 2 inches by 2 inches, and it's got different roughnesses in different segments. This being a visual comparator, you can now, in this instance, use a magnifying glass, look at your surface, look at this comparator and say, does it conform to these 2 segments at the top, which will be a representation of something that's recorded as a fine measurement, or is it more within the next range, which is the next 2 down the side, which is then referred to as a medium profile, or is it across the bottom of the actual comparator, which will then refer to it as a coarse profile. And obviously anything less than the finest one, or anything coarser than the coarsest one, is referred to as a finer than fine reading or a coarser than coarse reading. Now, this is ASTM method A, and this is the most preferred method and less intrusive method of actually measuring the surface. But again, it's only a visual representation. The next one that you see is the most common one used in the industry, if you are allowed to use a gauge that is now not intrinsically safe, I can put it that way. So obviously the comparator used earlier, if you're in an area that you have to use an intrinsically safe instrument, that's the preferred method for measurement. And even if it's a curved surface, you can use a comparator for that. But using this type of gauge that you see on the screen here, which is a method C measure of measurement, you now have to take a representation of an entire area that you are measuring, taking quite a few different measurements and averaging those values. And there was an old method of measuring where you used to take 10 values and average all 10 values, and that's the measurement that you would have taken. And you would do this, repeat this 3 times. So that's 30 readings that you have averaged. But then they started picking up in the industry, because you are taking peak values and you're taking valley values, it's not a true representation of what the deepest valley is or what the highest pit is. So the new method of measurement is doing exactly the same, taking 10 readings, doing it 3 times, so that's 30 readings, but only recording the highest value that you achieved in each set of 10 readings. And by doing that, you now get to your third method, method C, according to ASTM D4417, which is using replica tape. And taking this replica tape is almost like an impression that a dentist would do. He puts that putty on top of the thing and shoves it into your mouth, and he tells you, bite down. So now you've bitten down on top of it. And what has he got? He's got an exact replica or imprint of what your teeth look like. And this is exactly what this little piece of tape does. It's a piece of tape that when you actually force it down onto the substrate will form an impression or a negative impression of what the value is of your profile in that area. And then by taking a measurement, you can accurately now measure what the profile is. But coming back to the method B measurement on ASTM D4417, because we had recorded those high values, your Testex tape would have also recorded the deepest pit. So now, if you compare your Testex tape value to your digital value that you had, there's more of a comparative between the two to say, now I can see, where previously if you used all 30 readings, it would have skewed those values down because it's actually taking an average of the highest bits. So these 3 different methods.
Thanks, Gert. And I think that where that's helpful is that if you don't know what your highest values are, the risk is that you're not going to put coating on enough to coat them. So I guess that it's really helpful that we don't just take an average, because that can be so skewed and you can end up with in worst case scenario, I'm imagining that you could end up with spikes of uncoated steel sticking above your coating if you haven't taken that into account. Just talking about applying the coating, we obviously spent quite a lot of time last time looking for pitfalls and gremlins associated with the application process. So coming back now, we've got our coating on our steel, and we now need to take thickness measurements, usually dry film thickness measurements. Let's talk about how we do that without causing a punch up, because everybody wants to do it their way.
Again, I think that the easiest method is to always refer to a standard. And the standard method, or the most common one used out there, is the SSPC PA2 standard, which is determining the conformance of your dry coating thickness requirements. So how does it evaluate and according to what am I painting at that point in time? And it's a non-destructive method of testing. There are destructive methods of measuring, but it is dealt with in a different standard. So this PA2 standard is the most common one that gets used. It's defined in different gauges that gets used. You even get something that's called a pencil gauge, and it looks exactly like a pencil, not like I'm holding now, but that's how small it is. And the reason for that is if you maybe want to measure rebar, something that's round and very small, you can get more or less a thickness to see if you're getting the coating. Then you get what's referred to as a type 1 gauge, which is a magnetic pull-off gauge, or more commonly referred to as a banana gauge. And then you get your type 2 gauge, which is an electronic type gauge. It uses batteries, obviously, and you can get a representation via eddy current methods of measuring, but it will measure your coating thickness quite accurately.
Surely we've moved beyond the banana gauge scenario. Surely we've moved into the electronic era.
You know, that's a question that I often get asked, especially when we do the CIP lectures. And the answer is no, because sometimes you're in an environment where you have to use an instrument that's intrinsically safe. And what is the only one that you can use? It's the banana gauge. Is it as accurate as the digital ones? Well, they're very accurate. They've got about a 7% accuracy compared to the 5% accuracy of the digital gauge. But the problem comes in, people don't know how to use it, and they don't know how to.
That's always the problem.
Most definitely. And when it comes to verifying calibration, to see, does my gauge measure up to what I'm busy measuring at the moment? That's where a lot of fighting or infighting can happen, as what you quite rightly mentioned.
So let's spend a little bit of time talking about calibration, Gert. There's so many variants. When I've been on site, this inspector says we must calibrate on a glass plate, and this inspector says, no, we must use another method. This one says we must use the instruments method. What is the answer, and how can we then be sure that my data gathered is as reliable as your data? Will it even be the same?
Again, the answer is yes, no. The most preferred method for any calibration or verification of calibration of a gauge is as per manufacturer. So I'd like using the analogy always and saying, if you drive a BMW, a Mercedes manual is not going to tell you how to drive a BMW. And a BMW manual isn't going to tell you how to drive a Polo, and so forth. So you refer to the manufacturer. But when it comes to, it has to have lubrication, or it has to have water, when it has to have fuel, they all have to meet a standard. So that standard method now for the type of fuel that gets used in a vehicle is the same across the board. And that's where SSPC PA2 is a very good standard to refer to. So if you had a measurement with a type of gauge, maybe a positector gauge on site, and I was using an alcometer, and somebody else was using a Fisher, and somebody else was using a Major Tech, and we're all getting different readings, PA2 brings us back to the same method of measuring. And quite rightly, you mentioned two different methods of measuring. This is what's done on a rough calibration. So a rough calibration is obviously your blasted surface. And the reason for doing that is because you want to measure coating thickness over the highest peak. Otherwise, you've got peaks that are sticking out of your coating. So what the gauge does, the electronic gauge, you need to set it up with a known shim or a coating of a known value over the highest peak. And that's this yellow thing that you see here on the steel plate. That's a plastic shim. And now you will adjust your gauge according to what that known thickness is. Once you've set this gauge up, then it will now record accurately. The ISO method is very similar, but instead of using the blasted panel, you will now just use a smooth, flat steel plate that's got no profile on, unblasted. And you would go through the same verification to make sure that your gauge is actually set up in accordance with those measurements. And then it's as simple as going and taking the measurements. But again, how and where do we take the measurements? I think that's the question.
That was going to be my question. Nothing is as simple as we like to think it is. So let's put us out of our misery and let's talk about how practically we should be taking our measurements. How many do we take? Where do we take them? How do we know we're doing it right?
PA2 has a standard method that you measure it again. What you're seeing there on your screen now is a representation of a page that is found in the SSPC PA2 standard. The blue outline that you see on the outside is a reference area of 10 square meters. So that's 10 meters by 10 meters. Each black spot that you see on there is a 4 centimeter circle in which the red dots is a single gauge reading. So according to the standard, it says that for every 10 square meters, you will take 5 spot measurements, which are the black circles, but in each spot, you will take 3 gauge readings. And averaging those gauge readings, you get an average per spot. And in averaging the spot measurements, you now get an average for the entire area. Now you evaluate it in accordance with your standard to say, with the specification, am I within what the thickness range is that was specified?
So we don't actually hold a single reading as the make or break of a coating application. And I think that's quite important for us to realize. Because we're taking an average of averages, we've discounted the fact that you might have a particularly high peak that doesn't have a coating that's as thick as a deep valley. But because we're taking that average of averages, so we now take the numbers that we've developed for our 10 square meters, and those are the numbers we decide, yes, this meets the specification, or no, this does not. Have I understood you correctly?
100% correct. And the reason for actually doing it in that area that we've shown in the picture before is that the standard method for measuring is doing it in those 5 spots. If I'm the inspector on site today, and then there's 2 different inspectors 3 weeks down the line and another inspector 3 weeks down the line, everybody can go back to an area and actually identify an area that needed repair. So the inspector might have pointed out that area 2 or area 3 or area 4 is low on dry film thickness. So when they do the next stage, they've got to go back and put an additional coat on those areas. But where is it? Nobody knows. So PA2 again now takes you back to that area and says, this was the area. It was area number 3, which was in the right top-hand corner, or it was in the left bottom corner. And if anybody that has done the CIP courses know, that is the preferred method for measurement. And you can now narrow it down even further and say, am I in conformance and how much do I need to build up in that area? But getting back to your comment that you made, never can you take a single gauge reading and say, I'm low in this area. It always has to be at least a minimum of 3 gauge readings in a 4 centimeter area in order for you to say this area is low or high. And then PA2 goes even further.
Okay, so I was going to say, so now we've got our readings, and now we're trying to see whether that falls within the window that we're allowed according to the specification. Let's say we had to be between 200 and 250 microns. How do I know? And my average comes out at 199. Do I fail it?
It depends. The reason being again is because the old PA2 standard allowed you any spot measurement. Now knowing what a spot measurement is, it's at 4 centimeter with 3 gauge readings as an average. That spot measurement was allowed to be 20% less than what was specified or 20% more than what was specified. But now again, and I'd like to just do a screenshot of the actual standard that depicts the restriction levels. The new standard, which is the 2016 version of the standard, now has minimum and maximum levels that are allowed. And as you can see, the level 3, which is the default, that said that you would allow a spot measurement that was 20% lower or 20% higher than what was specified. But the entire area, that entire 10 square meter area, when averaging all those values, it has to fall in with the specification. And as you can see with all of them there, we always go back to what was specified. But if you have a level 1 type of a restriction, you are not allowed outside that 200 to 250 microns, a range that you were given in your specification. Level 2, you're allowed to go a little bit thicker, but not thinner. Level 4, you're allowed to go outside thinner and even more on your maximum. You might now ask the question, what's the reason for these different levels? The reason being, like a level 1 type of a tolerance would be for tolerance fits. So if you've got a bolt and nut situation that have to fit in for shear strength, cannot go outside of what was specified on the total thickness that is required on that. And the same goes for aircraft and so forth, for imbalance and other scenarios. And that's the reason for the different restriction levels with the new PA2 that was set up.
And that does make sense, and probably quite wise of the specification writers to acknowledge that there are scenarios where actually going outside of the boundaries of the spec just cannot be accepted at all. Just thinking about that, so one actually has to be able to work out what your 80% and your 120% values are. And I know it sounds a little bit pathetic, but being able to do averages and so on is also really important. Your simple arithmetic functions are absolutely critical for the inspector to be competent at.
Most definitely. And talking about that, what do we follow? We need to follow what the specification tells us. And unfortunately, what happens is that we are given 2 documents. We've got our product data sheet and we've got our specification. Now, if your specification is vague and it says, do what the data sheet says, we must bear in mind that the product data sheet, the manufacturer would have designed it with an absolute minimum value that the coating is allowed to be applied at and the absolute maximum value. If you now apply that 80-120 rule to what the product data sheet says, you can have a coating that's as thin as 20 microns, but it can go up to 400 microns. That's a huge difference. And that's where the specification or the level of protection is so important. Remember in our first series, we spoke about 12944 and the restriction levels that you are again allowed there. The environment being a C1 to a C5 environment had different thicknesses specified, and they're very tight. It's normally 200 to 250, 200 to 300. So using the specification and calculating your 80-120 rule in accordance with that, that's important for the successful outcome of the coating that was applied on the substrate.